Okay, so welcome to this lab. Today we'll cover lab 7 and 8. Lab 7 is about implementing proportional controller and then PI controller. And lab 8, which is a continuation of lab 7, we are recording. And lab 8, which is a continuation of lab 7, which is a PID controller, we will be designing and implementing PID controller for the first order systems. Okay, then the equipment we will use MATLAB. Here we have an introduction about the lab. Okay, it defines what is the PID and then what is the PID, P and PI and PID controllers. Okay, then it starts by the definition of the PID controller, which is we covered in theory. Now the experimental setup, which is level liquid control. Then in this figure we have a level controller, okay, water level system. We have the control valve, we have the input, okay, and then we have the process variable, which is the height, and then we have the output, which is okay, the physical output, which is the flow. Okay, then H bar stands for the steady state. Okay, then Q bar here stands for the steady state flow. H bar stands for the level, liquid level, steady state. Okay, and then Q out, which is the steady state flow out. Okay, then we have the definitions here. We have QI, QO, small letters. Those are the small deviation of flow rate, inlet, slow deviation of the outflow. H is the small deviation of the head from the steady state, and R is the resistance of the fluid flow, and C is the capacitance. Okay. Then the first question, part 1, which is derive the mathematical model of the system to control the level of the fluid, okay, H of S, and derive the mathematical model of the system to control the output flow. Okay, then here in this system we can either, for example, we can take the process variable as the height, okay, level flow, or we can consider the output flow. Okay, then this is part 1. You will have to derive it, but I included this for you. Okay, then you will see this this document is attached in the file itself. Okay, and then it shows step by step how you can derive it. Okay, and then you have here, for example, the definitions for each parameter. Okay, then it will start from here. Okay, then those we already covered them in theory. You just have to go back and then learn how to derive them, and then you'll see here. Okay, this is by mistake. Should not be. Okay, then here we have. Okay, then this. Okay, then this is the transfer function for the level control, and this is the transfer function for the flow control. Okay, then this should not take a long time with you. Then I cross this. Okay, then this is belongs to the 2 degrees of freedom water tank. Okay, then this is something you will find attached to. Now I'll go directly to part number 2. Okay, part number 2, it says create the open loop Simulink model to control the level of the fluid in the tank with no controller, okay, and subject to a unit step signal. Okay, now we have here H, the transfer function. I just have to model this into the Simulink. Okay, then to start with this, I would start with Simulink. I'll start blank model. Okay, there we go. Okay, then I would save this. Lab 7 demo. Okay, then first of all, I have to include the transfer function, then transfer function. Okay, then double click on it. And then for here, I have R, and then the time constant is RC, right? Then for myself, I have the values R half, and then C is 1. Then here directly I can write, okay, RC, that is half. This is stands for R. Okay, and then for RC, R times C. Okay, then you can multiply them. Okay, for example, that is half for me times 1. Okay, and then the second is 1. Apply OK. Okay, then here I have it. I think this should be fine. Okay, then times 1, or either directly I can write it. Okay, it should be fine, I think. And now I will add scope. Okay, and then I can add the step signal. Okay, then here I can write the step point. Okay, and then also I can add, okay, max. Okay, then this is, because I will have more than one signal. Okay, for example, I would add the set point because I want to compare it always to the set point. Okay, and then I will add here this. Okay, you can scale it the way you want. Okay, now this is the transfer function. We can write this is, okay, math model. This is the mathematical model. Okay, and this is, we can call it the open loop. Okay, open loop. Because I will have to view it. Okay, now if I run, okay, then here I can see, then view, I will insert the legend. I can see the step point, which is in yellow, okay, and then the open loop response. I can see them, right? Now for myself, I can see clearly for myself here, because if you see the G0, which is half over 1, right? Then I have an error of, okay, an error of half. Okay, then that is for the open loop. Now what should I do here? Then I will have to answer those questions. Okay, then snapshot the Simulink model. Okay, then that is the Simulink model. You can take screenshot. Okay, and then add it here. Okay, then right click, you can crop. Okay, make it neat and clean. Okay, then that is the, for the open loop. Now I need to submit the response, right? Also the response, there are different ways. Okay, for example, you can save this as, okay, or you can print it, or print to figure. There are different ways, and also you can make screenshot as well. Okay, as long as it is good and neat, you will get the grade. Okay, don't leave it like this. Okay, don't leave it like the way, do it the way I'm doing this. Okay, and scale it to the page, because I need to look into the details. Okay, scale it to the page.
Step response.
This for what? Okay.
It's okay.
No, show me what you have.
RS 10 and SS 15. Make the time 1000.
It should be fine because you have the minus error. Okay, just follow now. Okay, then next. Then that was part 2. Then for part 3, design. Okay, now design analytically the closed loop system with a proportional controller. Okay, KB to control the fluid level with steady state value of greater than 0.5. Okay, then if you remember, in LO2, right? In LO2 we have Okay, okay, then this is handout number 3. This is for error. No, it was okay. L04, right? L04 handout 2. And then for the L04, you will have to design the system manual. Okay, then KB, you don't know it, but you know you want to get the steady state, which is 0.9. Okay, then you will need to design the controller, which is here. Okay, then HOS is 1, and then you want to design the controller in order to have the steady state value, which is 0.9. Okay, then that means if you are okay for the closed loop. Okay, let me take copy of this. Okay, I will copy this. Okay, and then here I will add the summation point. Okay, then double click on this. Here, minus, right? And then, okay, and then here, normally I will have to add gain, okay, or gain or PID. Okay, then here, double click. And then I will have here only proportional, right? Proportional, which has a value of, now this, I will make it 3. Okay, and then this is the closed loop, and then proportional, P, closed loop. Okay, and now I will close the system, give feedback. Okay, and then it will receive a signal, which is the set point. Okay, then now the system has a feedback, because here you have K, right? K, yeah. Then if the G0 K times the transfer function will be 0.9. Okay, then you'll have to find the K value here. Okay, which is, if you remember, yeah, you want to find the K, which make the response, okay, or the steady state value 0.9. Okay, then this is, you have to solve it by hand, analytical. Greater than 0.9. Okay, but I would say I will calculate for 0.9. Then if I want to take the transfer function, okay, then here, for example, if I say and then see the steady state value for the open loop, which is G0. Okay, now the what I have here, I will have Okay, I will have K for the gain. Okay, then for myself, this is 0.5 divided by 0.5 will be equal to 0.9. Okay, then if I want to find the value, okay, when G0 okay, G0 would be this times 0, right? Then I will have half, okay, half K times 0.9, and then from this, then 0.9 okay, then K would be 0.9 divided by 0.5, okay, which is 1.8. Okay, then that is the gain for my case. Okay, now if I run here, I have the value already. I have it for K is 1. Okay, just make it like, see now the closed loop is worse with the K1, right? With the K1, the closed loop is 1. Now if I change K to, okay, 1.8, okay, then here I have some improvements, right? I have some improvements. That means I will have to increase the K. Let us calculate. Okay, if we calculate the transfer function, closed loop transfer function, what it would be? 1, right? It would be, okay, K times the transfer function, which is this, right? And then the whole thing would be divided by, let me draw here. Then for the closed loop, I will have K. Okay, and then here I have half over half S plus 1. Okay, then the transfer function for this would be K times half, right, over half S plus 1 divided by 1 plus 1 plus half divided by half s plus 1. Okay, and then this is would be k times half divided by half s plus 1 divided by half s plus 1, right, plus half, and then the whole thing divided by half s plus 1. Then this is will cancel, and then I will get k times half, okay, divided by half s plus 1.5, right? This is would be equal to 0.9, because if you remember the rule for we have 1 over 1 plus kb, right? This is should be equal to 0.9. If you remember, we have this. Where is the formula sheet? This is the formula sheet. This right here for the type 0. This is type 0. Then or directly from the type 0 definition, 1 over plus kb, which is 1 over plus g0, which is g0. I got for this g0 is 1 plus, okay, here I have half k. Okay, this is the g0 will be equal to 0.9. Okay, and then if you solve this, one over 0.9 is equal 1 plus 0.5 k. Okay, 1 divided by 0.9, 1. Then this is would be, okay, 1 divided by 9 over 10, which is equal 1.5 k. And here I will have 10 divided by 9, which is equal to 1 plus half k. Okay, and yeah, then here I will have 10 minus 1 over 9 half k. Okay, and then no, 10 minus, sorry. Okay, 10 over 9 minus 9 over 9, which is, this is the one, huh? Equals 0.5 k. And then from this, I will have 10 minus 9 is equal 1 over 9 equals half. Okay, and then k would be okay, 1, right? K would be 1 divided by half k times 9, right? Okay, k times half times 9. Okay, and then this is, no, there is something wrong here. Okay, then let's take this. Yeah, then here I will have, and then that is the error. Okay, this is, we are calculating here the error. No, instead, yeah, we did a mistake. Instead of 0.9, instead of 9, we should have took 0.1 because we are calculating the. Okay, let me repeat here. Okay, then here I will have 0.9, which is the error, right? That is the error. Okay, then here I will have 1 over 10. Okay, then here I will have 1, right? And then here I will have 10. Okay, 10 minus 1, right? 10 minus 1 is equal to half. And then I will have 9. And then k would be equal to k would be equal 9 divided by half, which is 18. Okay, which is 18. Okay, because we got, then let me plug this here, 18. Okay, and then now it's good. We are good. If I want to measure it, okay, then I will add cursor measurement. Okay, then on the screen. Now, if I take this a little bit here, okay, then you can see here it reads 0.9. Okay, then either ways you can calculate it this way. Either, for example, you can use this, which is the that stands for the steady state error. You can calculate, or you can reduce this. Okay, you can reduce this, and then you find, we say the steady state error 0.9, and then you calculate k from it. Okay, now validate your work. That means, okay, just you'll have to, as I did. Okay, I tried the 19. Okay, and then I got it right. Okay, then I get it right, which is working for me. Okay, then I would take now a snapshot for the Simulink. Okay, you can take snapshot for the Simulink. Okay, then you will have to, as I said, you will have to make this clean. Okay, and then also I will snapshot the answer. Okay, now for example, you see number 1, it reads the open loop. Okay, number 1, you see here the values, okay, this is the value for the steady state, half. Okay, I can take screenshot for this. Okay, and then add it here as well. Okay, now we go for part 5. Okay, part 5, the design analytically closed loop system with the PI controller, KB and KI, to control the fluid with overshoot 0.10%, okay, and then settling time 0.2 seconds. Okay, then this is we have where we have to do it, how to do it. Okay, then you have to follow this example. Okay, in this example we have the transfer function, and then you have already the transfer function for you, and this is the PI. Okay, you will have to follow those to solve here, right? Then for our example, you are given an overshoot 10%, right? 10%, you will have to look into here. Okay, then if using this equation, you have the overshoot, you can calculate zeta. Okay, once you calculate zeta, okay, once you calculate zeta, and then here you have the other value is the settling time. Okay, then you have the settling time, right? And then you have zeta, you can calculate omega n. Once you have those, you are done. You can calculate the Ki and Kb for your system. Okay, and then you will have the controller, which is you'll have those values. Okay, this is this example we explained in the class last time in the theory. Okay, it is the same. Now here you have the transfer function for your case. You'll have to design, you will have to follow this. Okay, up to here, you will have, okay, you will have to use this to calculate zeta based on the overshoot. And then you have the settling time. For the settling time, you will use this. And then you will calculate omega, and then from this you will be able to calculate KB and Ki. Okay, then what I will do next, I will make this is 4. Okay, again, I will copy this. Okay, and this is closed loop PI. Okay, and then here I will have to choose you will have to choose your values. Okay, then PI, and then what you got, for example, from theory, you will have to input here. Okay, now for example, okay, for example, for my case, I got okay something like 19 and 223. Before applying this, okay, if I apply, for example, 1, and then before I had 18, right? Just leave this as it is. If I do the simulation, look. Okay, now see, for the green one, which is the PI, right? We can see after 10 minutes, okay, 10 seconds, maybe I will need to zoom in. If I increase the time, for example, to see what will happen next. Now see, it will approach the value 1, okay? But Okay, I will have to put my values, the one I designed the system for, 233. Okay, see, I will make just 5 seconds in order to zoom. See, before that was, okay, it was going like this, right? Ramping. Okay, so what we see here for the PI, it has eliminated, okay, it has eliminated the error, okay? Then, but there is overshooting, okay? There is an overshooting. You'll have to calculate this overshooting, for example, how we can calculate it. You can go up to this point, right? And then measure it. For example, you can see this value for me is 1.1756. Okay, then that means the overshooting for my case is 17.6. Okay, 17.6. And also, where is the number 2? Okay, it says, okay, then for example, the overshoot. Then for this you can, okay, we can simply, for example, make the sampling time smaller, 0.01. Okay, then here I can see now the peak time, right, and then the overshoot. You can see the time here, 1.163, and then the overshoot, which is this value. Now already we see big improvements. And then here also you'll have to, okay, then here you'll have to write down, okay, analytical, that means you'll have to design the system. Okay, question 6, we'll have to screenshot this. Okay, and then we have to screenshot the response. That is the response. Okay, now here we come to data collection and observation, values for the gain. Okay, then here, for example, how much you got for the for question number where I calculated the gain. Okay, for me, for example, the gain was 18, and then here it was 19. Okay, I can write KB was 19 and KI was 233. Okay, and then the steady state value, I will have to write the fill this out. Any questions? Okay, now for example, for each case, you'll have to fill it as you go. Okay, you'll have to find those values. Yeah, you can. Okay, then this is how you can do it. Okay, now for example, as I said, okay, then here you have measurements, right? For example, let's say you are starting with, okay, only with the open loop, right? This was the response for the open loop. Now for the open loop, okay, what was the steady state value? It was here. which is 0.1, right? You can see it, which was 0.1. Okay, and then also you can click on the signal statistics, right? You can see here, for example, signal statistics. Okay, signal statistics. Okay, see, now here you can select, okay, which one you want to, which signal you want to acquire. Okay, then I will acquire about the open loop. Okay, now for the open loop, it says here, the maximum, which is the steady state, right? That is 5, 10 power minus 1. That means it is half, okay? Okay, other statistics, for example, for the PI. Okay, then the maximum, here you can see the maximum 1.778, right? Which is this peak, right? At which time, this is 1.156, which is the peak time here. It measures it. Okay, see, for example, it calculates the overshooting. Okay, and then it calculates the raise time. See the raise time. Okay, then the raise time, you can see it here, 61.88 milliseconds. Okay, in milliseconds. Okay, then all here under tools, measurements. Okay, and then also beside this, you have the cursor measurements as well. Okay, then you'll have to fill this out, and then afterwards, there is the discussion. Okay, there is the discussion. You will have to discuss the result obtained, okay, and for the P and PI. Okay, for example, what is the, you will discuss those values, okay, the findings here, what happened when you use P and then open loop and then proportional and then PI controllers. Okay, then here provide a brief overview of what you have gained from this lab objectives and how it aligns with the theoretical knowledge. Okay, then that is something like a reflection. Okay, you'll have to write 2-3 lines, not more than this. Okay, then that is lab 7. Now lab 8 is a continuation of this lab, okay, which is in which I will have to design, okay, I will have to design PDI controller, okay. Then I would copy this as well. Okay, and then I will connect this. I will make this 5. And now instead, okay, now this is PID. Okay, and then here I will have to change to PID. Okay, then I will apply. Okay, if I run it without anything, okay, no changes, then we will see what is the response for the PID. Right, it is the same because I changed nothing. Okay, I changed nothing. It is same as PID. Now what I will do, I will go back here. Okay, and then I will auto tune this. Okay, then here you will not do any theory, it's just practical. Then here I have a tuner. Now, as you see here, I have PI, okay? Then PI, that was the, okay? Then this would be the starting point. Okay, it's not, now it's starting to open. Okay, and this is here, it's PID controller. Okay, then what we see here, we see, okay, the dashed one, which is the block response, okay, then that is the PI. And it's always comparing it with the tuned response, okay? Then the question, what does it say? It says, design PID controller, KI, KB, KD, and KI, that is with the minimum overshoot, okay, while maintaining the best settling time that you got from TS, okay? And then I want to keep those. Now, if I click on show parameters, then it will show me, okay, it will show me then the block, which is the one I have already, that is 19233, right? And then it is compared with the PID here. And then here I will have, okay, I have the rising time, settling time, overshoot, right? And then this is another way, for example, if you remember for the PI, you can come here and then click on the show parameters. It will give you all the parameters, okay? If you don't want to follow the method I show. Then to start to tune it, I have here the response time, okay? Then as I increase it, okay, see, as I increase it, the system is becoming faster, okay? See, the system is becoming faster. I have always the same performance with less overshoot, okay? Now I will have to minimize the overshoot. Okay, then that is the objective, to make it as less as you can. See here, if, okay, then I want to keep the settling time, okay, it was 0.3, right? Okay, then almost I'm there. If you make it faster, see, if you make it faster, and then the overshoot, okay, will increase. Then I don't want to make it faster. You can always reset the design. If you do a mistake, for example, or something, you can reset the design, and then it will go back to the beginning. Okay, then here. Okay, then now I want to. Okay, then that is, for example. Okay, now I think this is good. Okay, once I'm done, I can update the block. Okay, then once you update, you will have those values. Okay, then when you close it, okay, and then close, and then here you have the new values you can apply. Okay, okay, and then you can run the system again. Okay, see, for example, now I have the response for. Now I have almost the same performance. Okay, and then the best overshoot. Okay, by this, now you want to make also screenshots for the last one. Okay, and then the responses. Make the responses. Okay, and then here you will have to carry, for example, in lab 7, you have already filled this, right? Okay, you just keep them as they are, and then here you will have to fill the new values. Okay, new values, and then you will have to complete. You will have to write the analysis and discussion, and then conclusion. Okay, and then by this you will finish lab 7 and 8. Okay, as you see, lab 8 is short, yani only completion of lab 8. Any questions?
The practical exam will come like this, or easier or harder?
Okay, just something related to the lab. Any questions? Because this is recorded. No questions? Okay, I would now.